everyone. Welcome to our stories behind products number 8. So you may or may not have heard about sous vide cooking. This type of cooking has become popular in the last few years and is associated with modernist cooking. My name is Oya Demirbilek and I'm a professor of industrial design at UNSW. I welcome you from Little Bay, the beautiful Bijikul country where I live and work, and acknowledge the Bijikul people who are the traditional custodians of this unceded land. I would also like to pay my respect to elders, both past and present. So this evening, our presenter is Greg Upston. Welcome, Greg.
Thank you. Thank you.
It's so nice to have you here. Greg is principal designer with Breville, an Australian publicly listed company with a group of global subsidiaries leading small electrical appliances in the consumer products industry. And Greg graduated from UNSW Industrial Design Honors, and he has had consultancy experience in various fields from medical to street furniture and several years in the film industry. And after finding a home with Breville 15 years ago, he has been involved in developing many projects for the company. So Greg will share the design journey of the Breville PolyScience HydroPro Plus. And this is a feature-packed sous vide immersion circulator designed for commercial kitchens. So I will now hand over to Greg. Greg, over to you.
Thank you, Oya. Okay, so welcome guys, thank you for coming along. This is going to be the story of the development of the HydroPro Plus, which is an immersion circulator that we developed with Breville and PolyScience. So what exactly is sous vide? It's a process where the food is sealed in a pouch under vacuum and placed in a water bath, and we control the temperature of the water precisely so that the outcome of the cooked product is very specific to a temperature. It means under vacuum in French, and that was kind of where it originated. So when you think about traditional cooking, we have a high set temperature and a target temperature that we're trying to hit, and the food takes on that temperature quite rapidly, and then we control the time precisely. So by pulling the food off the heat at a certain point, the trajectory is changed and we end up at the target. One of the drawbacks of this is that if you don't control the time accurately, you either overshoot or undershoot. So the advantage, or one of the advantages of sous vide, is that the set temperature of the water bath is at the specific temperature that you're trying to hit. So for example, a steak, you may be aiming for 64 degrees. So the temperature of the bath is 64 degrees, and then we place the food in the pouch in the water bath, and it takes on that temperature until it hits 65 degrees. So you can't overcook using sous vide technique. What it also does is relaxes the requirement on the time. So the amount of time it spends in the bath after it hits that required temperature becomes less important. It gives you more tolerance on that time. It delivers consistent, repeatable, and predictable results. And it's favored by like restaurants, and it's becoming more popular since its kind of development in the 1960s. What we know is that certain temperatures, specific things happen within the food. So for example, if we look at vegetables, the pectin within the vegetable will start to break down at 85 degrees. So below 85, the pectin is basically the glue that holds the structure together. So under like 85 degrees, nothing really happens to the pectin, and you just have a warm vegetable. And then after that, it starts to break down, and the hotter it gets, the more rapidly it breaks down. But at the 85 degrees, you're able to like hit that point where the pectin is breaking down and control it very specifically. So we're using like specific temperatures to control the outcome. I think the eggs are a good example. So you can see on this chart on the right, as we change the temperature from like very small changes, 60 degrees, 62, 63, the structure of the egg is changing, and you can really like pinpoint the exact desired outcome for the product that you're cooking and control it with a specific temperature. Different things cook at different temperatures, and we need to control across a range and control that precisely, like within 1 degree of accuracy. Our units are like capable of better than that, but really, like, you can see the change that 1 degree would make. The other advantage, or another advantage of sous vide, is that you can secure the flavors and within the bag that you're cooking within, so you can retain and infuse more flavors in the final product. Okay, so PolyScience. So around 2007, the story goes that Matthias Merges, the head chef at Charlie Trotter's restaurant in Chicago, which was a hatted restaurant at the time, I believe, was looking for a device to use in his kitchen to investigate and use this new technique that was coming out of Europe at the time. Philip Preston, the owner of PolyScience, which was a scientific equipment supplier, developed an immersion circulator for chefs in the US because nothing was available at the time for commercial kitchens. And at that time, like around 2007, sous vide kind of stayed quite specialized within the commercial world, within quality restaurants especially. Around 2010, there were more commercial circulators for that industry, for restaurant industry. And a lot of these were quite fabricated. They looked like scientific equipment. The price points were like above $1,000, so the entry level was quite high, but they were available, you know, in numbers. Go to the next. So around 2011, PolyScience released the Chef series with a patented construction and legendary performance. It was like 1,000 watts, 30-liter maximum vessel, like maximum bath, 12 liters per minute flow rate. And it was priced around $800. And chefs really took to it. Like, it became the best-selling sous vide device globally at that time. A little bit more background. So about 2010, a gentleman called Douglas Baldwin, who's a certified genius, wrote this book called Sous Vide for the Home Cook. And what he did was took some really complicated maths about the way that food takes on temperature from the water, and also the way the pathogens or the bacteria within the food die over time due to the heat. And he distilled it into some understandable charts that people could use in reference, which made the whole sous vide process a lot more accessible and kind of opened up to more people, and kind of democratized what the process into, you know, other restaurants. So around 2012, Douglas Baldwin worked with PolyScience, and PolyScience released an app with algorithms called the Sous Vide Toolbox. This was like a phone or tablet-based app, and it could calculate the time to core temperature and the pathogen reduction logs. So basically, you could put in the type of food you're cooking, the desired result, like medium rare in this instance, 59 degrees, and the size and the geometry of the food, and it would calculate how long it took to reach core temperature, also how long it took to pasteurize and take out the potential pathogens. So this advancement it was making sous vide cooking safe and accurate, and was enabling these really complex calculations to be done in a user-friendly way and giving chefs the information they needed. Around 2012, crowdsourcing kind of got started, and sous vide was kind of one of the first areas where it took off. On the left here, 2012, that's the first Nomiku unit. In the center around 2013, there was the Innova and the Sancerre, and on the right is the Innova Precision around 2014. These are all very domestically marketed products, but and the Innova especially developed a community, so it kind of expanded people's appreciation for sous vide. They built communities and started to share across the internet, like ways of cooking. That end of the market, the domestic end of the market, got crowded really quickly. It kind of got flooded with the quickly Me Too products, and the designs were either like very generic or some kind of questionable design choices were made. It was quite easy to pick up a sample and have it rebranded and sell it into your market. And one thing I'll draw your attention to here is that spring clamps are kind of everywhere. We'll reference that later. I think the standout in this end of the market is the Chef Steps Jewel, which they released in 2016. It was a really interesting technical package. It was really nicely designed. Had a headlessly, so it was headless. You had to be operated through a phone app using Wi-Fi. It had this really small, more powerful heater. So this heater here is 1100 watts, which is 30% again on top of what the Chef series was. It was able to do low water volumes, and it opened up new possibilities and kind of, gave this more professional feel and approach to sous vide cooking in the home, in the domestic market. They had a really nice app too, which kind of showed the different textures of the food that you were targeting. So back to PolyScience. PolyScience was principally commercial. So this was their range at the time. This is around 2015, I believe. This was their range, and they had 3 Immersion Circulators. They had the Classic series, which they had developed first. They had the Chef series, which came on board a bit later. And they had a cheaper version called the Creative series, which didn't really take off. So Breville, when Breville acquired PolyScience, the first product we developed through that avenue was the Control Freak. I didn't work on this project, but it's a beautiful piece of kit. What it does is control the temperature within the pan very specifically. It has a temperature sensor on the cooking surface here, and it has a temperature sensor that you can put into the bowl. And you can target a temperature and hold it at a specific temperature by the way that they use the induction coil. It's very robust construction. It's durable materials, easy to use, easy to clean, and it has NSF approval, which is a commercial cleaning kind of compliance. The next thing we did was to redesign the smoking gun. So PolyScience had this smoking gun in the top right, and we redeveloped that. So the smoking gun was a convenient way to add smoke flavor to food without, needing to have a large smoking unit. Again, it's like robust construction, quality materials featuring stainless and like high quality polymers, easy to use, easy to clean, built to last, beautiful, and no tools for cleaning. So we were starting to develop a design language for and identity for the PolyScience brand, and this is going to influence the direction in which we took the circulator. That's why I'm kind of backgrounding at the moment to show you what we were thinking. So, you know, through the material and the detailing and the form, we were building a language. So next we looked to redesign the chef series. At this stage, this product was around 10 years old, and Breville PolyScience had engaged a consultancy to investigate the feasibility for the successor for the chef series. One of the issues that it had is that the shaft on the inside had an immersed seal. So the seal on the shaft was under the water, and there were some issues with that. It could fail over time. It could be replaced, but we were looking to kind of find a solution around that. And the pump was hard to clean. So for example, if a bag or an egg broke whilst cooking, it would suck the material through the pump, and it was difficult to access and get inside and clean that pump out. So that was another kind of early pain point that was looking to be addressed. So within the body of work that the consultancy did, they developed this really innovative solution for using a thick film heater. I'll explain that a little bit further later on. And excuse me. The novelty in this pump that they developed was that the inlet and the outlet are both at the same end. So it draws water up through the center of the shaft, turns it over at the top, and pumps it down and out through the side. They had developed this basically a proof of concept. So they had it working on a shaft, and they'd proposed like using this magnetic coupling, which was really novel, like a really nice kind of clean solution. And we liked where this was heading. So at the start of the project for me, we had, you know, an almost blank sheet. We actually had quite a detailed list of specifications already developed. So it had to be waterproof, IPX7. We had to have really good control over the temperature of the water, like plus or minus 0.1. It had to be able to service a large body of water. 45 liters was our target, and that required a powerful heater with a high flow rate so that we could move the water around and keep it stable. So throughout the bath, we could have enough turbulence within the water, within the bath, that there were no dark spots where the cooler water could hide. It's also really valuable to have a high-powered heater and good flow rate, in the sense that if, especially in a commercial kitchen, like somebody might drop, you know, 10 pieces of chicken wrapped direct from the fridge. So you have a mass of food at 4 or less degrees going into your water bath that you're trying to hold stable to a specific temperature. So having a powerful heater allows us to like respond quickly to that drop in temperature. And the flow rate means that we can pump that water through very quickly and keep it all warm, keep it all to the targeted temperature. Some other things that we needed were support for data logging for HACCP compliance. And I can explain that a bit more soon. And some general guidelines. They wanted a robust commercial design. They wanted heavier, more masculine, angular accents, heavier clamp, and possibly a lever clamp. So we had some guidelines, some quite detailed guidelines, and some very somewhat demanding specifications. Which brings us to, what does it look like? This is the fun bit for me. You know, as a designer, this is where we like to dwell. So basically, the start of the project, I just started collecting ideas. We were kind of bouncing around, you know, what it could be, just trying to capture the ways to deal with the screen and the leg, what size screen we should be using. We're kind of looking at other things like bottom corner here, like my S7 phone at the time and iPhone 5, like the smallest screen we thought we might be able to get away with, how that screen was oriented, how the device was going to kind of interact with the vessel. We drew on the consultancy work to kind of develop some initial CAD of their concept and what that might end up being in terms of size, and just to get a sense of scale and understand where we might be headed. So we continued just like capturing ideas. I was working on a different project at the time and I was kind of transitioning over, but you know, the cogs were turning and we started to like just throw down ideas of what we might be able to do and flick sketches around. These didn't have to be very detailed at the time because it was kind of loose and we were just looking for a something. So we were thinking like transitions in the leg from square to round, maybe how the head integrates to the leg. Maybe we could like introduce some stainless steel into the upper housing for that added toughness and wear resistance, where the part lines were going to go, how it would kind of start fitting together. Just variations, basically trying to explore what might be possible. None of these are like particularly good sketches, but they were just, the intention was just to capture ideas. How could we stand out from the crowd? And then starting to think on like a more detailed kind of level as to, you know, some of the finer points, like the foot, how that was going to work. Maybe we could offset the screen to one side. These just quick communications. From here, we started, well, this was actually David sketching. So he put together some initial concepts, and we started to develop an idea of the overall aesthetic we're looking for. So we decided that it needed to be round, the leg, because of the sealing requirement to meet the IPX7. And we wanted it to look tough and capable, kind of like a tool, like something you could trust, something that was, you know, capable of withstanding knocks. At this stage, we're thinking that we could have a touch screen, and we're thinking maybe screws on the front for that kind of hardened feel, or like general overall smooth surfaces. Just trying to flesh out what we might think, what direction it might take. We pretty quickly just modeled that and made something so that we could 3D print, rough paint, and get initial idea of like the scale and kind of where it's at, how it compared to the Chef series. We wanted to separate it from the domestic market, so we didn't want to do more Me Too domestic market product. We wanted to stand alone and look commercial. From there, we were still exploring and playing with concepts. We actually moved away from the touchscreen quite quickly because the preliminary research was showing that the cost was prohibitive. And at the time, Breville didn't have, I think we only had one touchscreen product on the market. So we're very hesitant about the development process and what that might entail and the cost we were kind of building into it. So we decided to go with, initially with a TFT and a capacitive touchscreen, capacitive buttons. At the same time, we're starting to think about the construction. So how we could leverage like the stainless steel tube for the strength. We knew we had to pass an IPX7 submersible test. So in order to pass that, you have to drop the product onto the floor 4 times from a meter and then put it underwater for half an hour, under a meter of water for half an hour. So we were like thinking about how we could build it strong enough to pass that test from the very beginning, and trying to trying to like use the stainless steel tube, so pulling in the fixtures from either end and making the stainless steel tube like the strongest element that would enable us to pass that test. Because we'd gone to the kind of capacitive TFT direction, the capacitive buttons in the TFT, we were looking at like ways of doing this front housing, and we'd done so on the control freak on the left here. That main control panel is a in-mold decal, so IMD, which is a PET skin, very scratch resistant, molded with a copolyester, which is a very tough polymer. And basically what happens is you print onto the PET skin and then vac format and overmold it. So you get this really nice kind of graphics resolved in that part, and it's tough and it's strong. We thought that direction would be really nice for where we were trying to take this, and so then again, David was like exploring ways of kind of making this bumper rim, like using that front molding that we had at the IMD, and making like this really kind of strong element which wrapped around the head to make it look stronger, tougher, basically. We were looking at like the angle of the screen, how the relationship of the front to the back, kind of just kind of working through more details. We transformed like the sketches into quick CAD, and then we made one, and it kind of didn't work. It was we call it the soap bar. It just wasn't really working for us. It didn't look intelligent. It didn't look very techy. It kind of looked old. Maybe not the right colors here, but yeah, it was one of those directions that we were willing to let go of. So around the same time, we were talking to the IMD suppliers, and there was actually a limitation on the depth that they could make that front housing, which meant that we pulled back the design. We're kind of working on this bezel and lowering the screen, but raising the bezel on the outside so that the screen was protected in, most instances if it took a knock. So again, we worked up, a design quickly in CAD, and it was looking kind of better. Around the same time, we were looking to, we were starting to get suppliers lined up. We were looking for screens. The problem with screens in appliances is that we need a long-term supply. Often it's easy to source a screen, but it's hard to guarantee like 5 or 8 years supply down the road. So we were screening suppliers, getting samples. At the same time, we were contacting like the thick film heating suppliers and trying to find one which was capable of doing the thick film heater on a tube. So just quickly on the thick film heater, what this is it's printed onto the tube in layers. So they print first I think maybe 2 layers of ceramic and bake that on, and then they print an element onto that. And then above that, there's like another layer to protect the element and insulate. So it's a printed PCB, basically. It's printed tracks onto the tube, and it basically, when you power it up, it becomes a big resistor and starts to heat up. It enables a very compact size with a very high watts density to operate. And that was what we were really interested in, like a very powerful compact unit. So at this time, like, we were continuing conversations with the supplier, trying to work out how this how the unit was going to go together, how it was going to assemble, like the assembly steps that are involved, whether or not we needed insulation, you know, where it was going to be sealed and how it was going to be sealed. We had this really nice concept for a foot, which was an investment cast part here. And then we had like a spring which had 3 flat sections on it. So it would clip on and off without a tool, and it would rotate and then stay. So yeah, like doing more conversations with the supplier, trying to work out how to make it. And here we were starting to get comfortable with this idea of like building from the heater up and then sliding the tube over and putting the head on and pulling it down. That was looking like a really robust solution. Excuse me for 1 second. So this is the IMD that we were working with, the IMD front panel. And we had our screen. We were relating what the screen looked like to what we'd done on the Control Freak in the early kind of concepts. And we were looking at how we could navigate through the requirements for this screen and what the input was going to be. So if we had plus and minus buttons to go through temperatures, it just would take ages. It wouldn't work at all. And so we're looking at like crosses, like slide designs to like, you know, or this kind of circular design, which is reminiscent of the iPod, which it was functional, but we didn't really want it to look like an iPod because like it was kind of old tech. It wasn't where we wanted to position it. We were also like, you know, just evaluating scale again and how it sat within the landscape. And we were starting to just make prototypes and test stuff. Like we were building circuit boards in the factory. The interface was a bit clunky. It wasn't really working. There were lots of issues we were working through, how to sense on the heater, how we were going to like pass the compliance requirements for a heater. And then a few things changed. So we had this impeller and it was kind of magic. It was magnetically coupled. So you insert it into the end of the leg and it would just take its position, and then you put the foot on and it was ready to go. However, it kept wearing out, right? So we had this kind of nicely resolved working impeller prototype, and we put it into the unit, and then we would start life testing and they would just die. They were wearing out here really quickly and then touching the underside of the lid and starting to seize up. We had lots of kind of materials issues. We went through lots of iterations to maybe change this into a peg or make it work in a different way. Less magnets, more magnets, different materials for the pins, titanium coatings, 316 versus 304, like lots of iterations. Where we ended up, and about the only thing that worked was a dual bearing. So this is like a commercial ruby, which is grown, I believe, and a tungsten carbide pin, which it runs in at the top. So the pin is centered at the top of the heater, and then the ruby sits and makes contact with that. So the only point that makes contact is the surface of the ruby, and with the magnets that allows it to rotate. And yeah, the only contact point is here, and both very hard wearing. And we were able to get some really outstanding kind of life test results using this system. For if I go back, one interesting thing that we had to do, because this is an enclosed tube at the bottom of the leg, when you put it into the water, it traps the air. So we had to work out how long we had to run the impeller to evacuate all the air. And we did multiple trials and multiple kind of prototypes and different impellers, different angles, different speeds, trying to work out how long it would take to get the air out of here, because we couldn't run the heater with air. It would start to create steam and issues. We were also looking at how low we could take the water level using this system. And you can see here, it kind of cavitates and picks up bubbles at us. You know, this is like pushing the limit of the water height. You know, we did multiple different options and trying to get water up to cool the bearing surface to stop the wear. Then we decided that we also needed probes. So this was kind of on the table and being talked about, but one of the requirements for the product was to have some sort of data logging to meet the HACCP compliance. So HACCP is the hazard analysis critical compliance point. So it's the process of managing food through its like from when it's received to when it's served, and documenting the temperature of that food at every point so that it's never within a danger zone for growing pathogens. To be able to log the food and produce a compliant HACCP report, we needed to know what the temperature of the food was, which required a probe. So using probes in sous vide wasn't new. It was around at the start, but it had kind of fallen off as people like started using the calculators and not the probes. So we were looking at how to, you know, initially, as from a design perspective at least, how to integrate it and use it on this. And we're kind of like making quick hacks, trying to work out how we could put it in and where we could put it in and what that meant to the form, etc. This is our initial kind of where we ended up as a starting point. These nice little pinch finger details, top mounted on the unit. Then we worked out that we received some legal advice on IP related to the placement of the triac. So that the triac is a switch which controls the power to the heater, and basically triacs get hot and they need to be cooled. So we'd initially put it on the heater surface because there was a lot of water moving through, and we knew the temperature of the water was like going to be less than 90 degrees. So we could at least keep the triac to 90 degrees. However, because of the advice on the IP, we had to look at and find a different solution. So we had to find a different place to put this triac and keep it cool. And we went through a whole kind of round of designs and trying to work out what the best solution was and where to put it. Eventually landing on using like an aluminium heatsink mounted to the inside of the tube, and using the water on the outside of the tube to draw the heat away from the triac. And then we were kind of like working out the details on how to do that and how to get it to be easy to manufacture. These were like heading towards the final result. Like on the right there, we eventually used a really nice solution that I think William developed at the time to pin the heatsink to the inside of the tube using this wire spring and like clips on either end, so we could clip it on the back end and then tuck the tips underneath, and it would secure it and hold it tight to the outside. Around the same time, and basically from the inception of the project, we were trying to work out how to put the Sous Vide Toolbox into the unit and how to be able to have this functionality on the unit, on the machine. And through the work that was being done at the time, like we got to a point where we decided that it was just way too complex to run it through this small screen and the circle track with the buttons that we had. We did some trials with this kind of arrangement, and what we found is that people were touching the screen trying to make their selections. I think part of the problem is that everybody has a mobile phone and they're used to like doing things in a certain way, and so I even found myself like trying to touch things to accept a command. So the other thing we realized at the time is that it was getting complicated, and it was going to be more complicated, and we really just didn't have the capacity to build the interface using buttons. So we decided we needed a touchscreen. We did some market research, and we put it before like chefs to kind of work out how they would feel about it and whether it would be acceptable. And with a very few minor caveats, they were generally on board with the idea. So we were developing, more CAD, adding the screws into the corner, trying to, at this stage, we're bringing the edges back and making it more kind of contemporary, squaring it up and kind of playing with the form and trying to build something which looked a bit more modern. We were looking at other IPX7 or submersible touchscreens and see what we could learn from them and how they were constructed, how the seals were built in, etc. We were breaking the screens because we were quite concerned about putting a touchscreen and then dropping it 4 times, whilst like a touchscreen on a phone being dropped is one thing, but imagine strapping a phone to a 2.5 liter bottle of milk and then dropping it. It's a kind of different story, and the impact. We wanted to try to understand how it would break, how it might break. Building visual models, trying to get an idea of like what size screen we wanted, etc. Because we were so worried about the drop test, we built a prototype to test it. And so basically the requirement is to do this 4 times and then put it in a bucket of water 1 meter deep. And you have to do it in different directions, like head first, bottom first.
Okay.
And then it has to go into the water and then, remain safe. You can see the foot coming off there, that's on a spring, so that's not actually a break. But we did find some issues. The prototype leaked. We weren't that concerned because it was a prototype. The seals were kind of all fabricated. But we found other issues, like the ruby was moving, or the washer on the ruby was moving off center, and we were getting some breakages. We basically kept dropping them to see where it was going to fail. So at this time we had a prototype. How are we doing for time, Oya?
It's 7:17, so you still have something like 10 minutes.
Okay, so I'll try and flash through from here. This is the eventual heat sink that we ended up with. We were doing things like pressurizing the unit, the prototype underwater to test the seals. So we'd run like the same pressure inverted. So the pressure at 1 meter deep, reverse, so positive 10 kPa, and try and get it to leak bubbles, and then track down where those bubbles were coming from, and we'll work on that seal. And one other concern we had was that if we completely sealed the TFT and then put it in an airplane and it was unpressurized, would it expand and pop? So we put it in a vacuum chamber and ran pressures of like equivalent to 30,000 feet. And we could see like the screens were bending. This is the glass that we use, which is a really strong kind of Gorilla Glass, high specification. So it was bending but not breaking, but the TFTs were being damaged. Eventually that meant that we couldn't completely seal the front side of the head. First off tool samples. And then we started wiring them up and testing them. We started life testing. By the end of the project, this room was like 4 layers of immersion circulators tall, just running life tests, trying to break things. You can see here the ruby bearing, which is in a silicon seat there, and the heat sink for the triac that I talked about earlier. So after a week at the factory reviewing the samples, we end up with like a massive issues list. And then we kind of go away and try and resolve all of these issues. So this was around the end of 2019. This is the functionality of the Sous Vide Toolbox. Like, I wasn't really involved heavily in the development of this. This was mainly like PolyScience, Dave P. and Conrad, and the UI team at Breville, Giselle and Vivid. But they did a fabulous job of just like making it really simple to walk through the number of inputs that you have to do to be able to like receive an accurate time, to work out the core temperature or to work out the pasteurization level. Once we had working units that were able to be like taken to the public, so we had, you know, working units with functional UX UI on it. We distributed them to chefs across this is the US kind of distribution, but we also did it in Europe and in Australia. And we gave it to them for like 4 weeks to use, and then went and did interviews and surveys and worked out what they liked, what they didn't like, and how we could improve working up or working through like towards, especially the UI, like how the UI was functioning. We're getting pretty close to time, so maybe I think, should we open to questions, Oya? What do you think?
I already opened it to questions, so I think you can just wrap up and maybe finish and tell us about what changes you made after these 4 weeks of trials with chefs.
So most of the changes were related to the UI and the interface. We were constantly solving problems throughout the whole project, and there was a large team working on it. We had teams across the world working on different aspects of the project. Yeah, so I don't have anything specific on that, but let's go to the questions maybe, and if I think of something, I'll come back to it.
Okay, so because there's no questions for now, but I will ask a few questions then. So it lasted 3 years or more than 3 years?
Yeah, we made a very rapid start. So we kind of started, I think, 2016, and we launched. Well, we were mostly completed by the end of 2019. So yeah, around 3 years project. We did do like a couple of big dog turns or turnarounds in the middle where we kind of changed the specification, and that delayed things. And yeah, we found certain issues that had to be solved during that development process, which kind of slowed things down. Like normally project is kind of 18 months to 2 years, but in this case, yeah, it took a little longer because of those changes.
Okay, so we still have some time, and you can ask your questions to Greg via the chat function. So Greg, if you can turn on your camera, we can see you.
Yep.
My other question would be, how much water do you need to have in the bath? How do you call the container?
Yeah, we call it a water bath. That's fine. So generally, you need enough water to cover the food product.
Mm-hmm.
We can heat up to 45 liters, which is of significant capacity. It's probably one of the largest in the commercial sector. Our flow rate is up towards 20 liters per minute, which means we can control that temperature very nicely, like within 0.1, 0.2 of a degrees C. Yeah.
Okay, thank you. So a question here from Jake Smith. Jake is asking, what was the involvement of the consultancy and how did their input influence the outcome?
Okay, so the consultancy was used, well, we actually used a couple of consultancies during the process, basically to fill resource that we didn't have at the time. So initially, we didn't have the resource. PolyScience was keen to move forward with the project, so they engaged the consultancy in Chicago. They did some really nice work investigating different ways of heating, kind of an initial spec, a kind of simple concept for construction, and they developed the impeller system, which we really like and continued to develop further. We also use consultants to optimize the impeller to work out how to make the aerofoils within the impeller more efficient to pump faster. We use different consultants to develop the firmware and the data logging app, which was developed in, like, it's Bluetooth connected. So yeah, like we use consultants. We also had consultants develop some initial concepts for the clamp based in Sydney. So we used them on this project where we were short of resource.
Okay, so another question from Anahita Jamshidi. Anahita asks, and she says, great prezo, Greg. Thank you. I think you mentioned one of the criteria you had for this project was to design a masculine product. And she says, apologies if I misheard this. And she says, I'm interested to know the rationale behind this criteria. Me too.
Maybe that's the wrong word to use. That was the word that came through on the spec sheet, so I used it. We wanted it to look like a tool. So we didn't want it to be fragile. And we had, like, the other two products that I showed, the Control Freak and the Smoking Gun, very robust, kind of tough looking, like nice materials, stainless steels and glass and like high grade polymers. So we were looking for that kind of tough aesthetic, not to say that only masculine is tough. Yeah, that was the word that was on the brief. So I actually just used that word, but I think what they were looking for was, you know, something that looked tool-like, that was not going to break easily.
Okay, so another question from Daniela Martinez. She says, what was the main difference for you designing for a commercial user rather than the domestic market?
The life testing was a lot longer. Like, we had to make it, the testing requirements were so much harder to pass. So the amount of, like, we had circulators running at 90 degrees, 24 hours from T1 until they broke. So we were running them, like, well, by the end of the project, they were probably in service for a year, constant. What we were trying to do is clock up as many hours as we could to understand what things were going to fail, and how to, like, catch those things and fix them before release. So I think the biggest, change from moving from domestic to commercial is the amount of use they get. It's all, it's also things like the environment of use and how they're kind of mistreated. Chefs aren't super nice with their products. So yeah, the demands of the product are different. Like, I think that's probably the biggest, and like, they want it to work all the time, use it easily. Like, the clamp that we developed, they love, because previous to that, they only had screw clamps, so it would take ages to, like, kind of fit and assemble. whereas we developed a really nice solution that was, you know, quick release and spring clamp on the back. I hope that answers your question. I'm not sure.
Thanks, Greg. There's another question from Ji Mang, and she says, great sharing, Greg. It's really nice to know how a product has been built up. I'm curious, how did you do the user feedback and what did you do to improve it? Anything to share with that? Thanks.
So yeah, like I said, we took product, we gave it to chefs that we sourced through I think the company was called Star Chefs, based out of the USA, and some chefs that we knew. Basically, we had chefs involved the whole way. Like, we were pulling chefs in all the time to kind of get feedback from the very beginning of the project. We worked with Aaron Teese in Sydney, who's Studio Neon, the suppliers in Australia, the suppliers from the USA, Dave P, who works with PolyScience, he's the marketing manager in the States, is a chef. We're getting as much input and feedback from them, like just giving them concepts and kind of working through and workshopping how we could improve it the whole time. In terms of the towards the end there, what I outlined, I think, so we gave the product to a bunch of chefs, about 15 in the States, I think, and then they used it for 4 weeks, and then Vivian and Giselle traveled and interviewed all of them, talked through like what they'd found. We had a research document with lots of questions on it, which we could use to kind of identify issues that were being found. You know, we found lots of things, like the impellers were breaking because they were dropping them, so we had to improve the strength of the impellers. There was some confusion over the difference between pasteurization and core temperature and why they needed to know it. Some of them didn't want to use the probe, some of them did want to use the probe. Yeah, so we kind of pocketed all that information, and then most of the changes after that stage were related to the user interface. I would say that we're pretty much locked in for the hardware, like from the consultation that we'd already done by that stage, and everyone was very happy with like the specification level. Like it's a really nice piece of kit. It does a lot. I hope that answers the question.
I'm sure it does. Thanks, Greg. Another question from Chris Hardy. He says, great presentation, Greg. Such an interesting and involved project with an amazing outcome. What would you say was the best takeaway for you? Something you are proud of? I think personally, like the way the team worked together was probably the best takeaway. Like, we solve problems all the time, right? Like we kind of deal with problems. We try to work out why things are breaking and then how to fix them. So having a really good, knowledgeable, experienced team, like I was one of maybe, I don't know, 60, 80 more people, but having access to experts in their field, being able to contribute and collectively solve problems, I think that really was the highlight. I hope that helps, Chris. I'm sure it does. And the final question from me, I know you were not involved in the user interface design, but from the top of your head, do you recall how many different tasks there were there? Because I gave a project to my students. I just want them to understand how many tasks there could be in a user interface in such a product.
Wow. It's incredibly complicated, I would say. I'm not a UI guy, the work they do is amazing. The number of iterations they go through and like the testing that they do, putting it in front of people, trying to work out how to make something intuitive and how to make all those tiny decisions, you know, jump out at you and be logical in that use situation. Hats off to the UI team and the UX team, like amazing work. I think the capability of the unit is amazing, and the level of resolution within that interface is something that I think we're all like incredibly proud of. I would invite you to go and have a look. Like the YouTube channel, the Breville commercial YouTube channel has some videos kind of talking about like the features, etc. Some more information on Sous Vide. PolyScience Culinary has lots of information. Breville Commercial will probably feed you here. Or if you have any other questions, reach out to me. That's also fine. I hope that helps, Oya.
Yes, fantastic. Thank you so much, Greg. A heartfelt thank you to you for generously sharing this excellent story with us. So thank you. That was amazing.
You're welcome. I kind of feel like I only scratched the
surface.
top of the eye. Yeah, like this. It was really hard to kind of pick what to talk about, and I think I probably like glanced over a lot of stuff that maybe I should have dwelt more on. But it was great opportunity. Thank you. I hope people enjoyed it. Yeah.
I'm sure they did. And also thank you to all our attendees this evening. Thank you for joining us and making the evening even more special with your presence and your questions. And that was our last talk for 2022, which was our second season for Stories Behind Products. And we will be back next year with a new program of products and speakers. So stay tuned for the invitations. And we look forward to seeing you all again next year for our third season of Stories Behind Products. Until then, be safe and well. Goodbye, everyone. And thanks again, Greg.
Welcome.